All right, so now we're going to look at the notion of stiff differential equations. Okay, so the question is, what are stiff ODEs? Okay. All right, so let's start with an motivating example, if you will. So let's consider the following example. Okay, so y prime is equal to lambda y at time 0 is y0, and then lambda has the following form, okay, minus 100, 1, 0, minus 1/10. Okay, and let's try to discretize this using the Euler method. And see what happens. Okay. All right. So what happens with the Euler discretization, of course, is that the solution at the new time y1 is equal to the solution at the old time y0 plus h times the vector field evaluated at the old time, which would be h times lambda y0. Okay. So this is really just equal to the identity plus h lambda multiplied to y0. Okay, and it's like you keep doing this. It's like, and you can basically show that yn is equal to 1 plus h lambda to the nth power times y0. Okay, so let's see how you can go about analyzing this. So I'm going to consider a spectral factorization of this coefficient matrix lambda. Okay, so I consider a spectral factorization. Okay, of lambda. So what basically happens then is that you transform essentially into a basis of eigenvectors, and then that allows you to factorize it as the conjugation of a diagonal matrix, where the diagonal matrix consists of the eigenvalues of the matrix. All right. Okay, so you get that lambda is equal to VD V inverse, where V consists of a matrix that's like which is composed, it's like of the eigenvectors, which looks like 1, 0, 1, 9, 9, 9 over 10. And then D is the diagonal matrix consisting of the eigenvalues of the matrix lambda. Okay, so D is going to be equal to minus 100, 0, 0, minus 1/10. Okay. So, the advantage, if you will, of doing a spectral factorization like this is that then you can obtain easily an exact solution of this differential equation, right? So from this, right, the exact solution is given by the following. Okay, so y of t is equal to e to the t times lambda applied to y0. Yeah. Okay, so this is just a general form of the solution of a non-autonomous linear differential equation. What happens is that when you do this spectral factorization, this exponential is easy to compute. Okay, so this just looks like, essentially, it just looks like the conjugation of the exponential of the diagonal where the conjugation is by this matrix V. So you get V e to the TD V inverse, okay, times y0, right? And of course, e to the td is easy to compute because d here is a diagonal matrix. So e to the td is just equal to e to the minus 100t, e to the minus 1 over 10 t 0, 0. Okay. So basically what happens is that y can be written as some linear combination of two solutions of the form e to the minus 100 times t times some vector x1, right, plus e to the minus t over 10 times a vector x2. So this is the general solution, if you will, of that linear differential equation. And of course, e to the minus 100t, it's like decays extremely fast, right? And this e to the minus t over 10 term decays much more slowly. Okay. So, all right, so that tells you again something about the solutions. And more or less what happens is that even after a moderate amount of time, the solution of the continuous differential equation is in some sense dominated by this term, which is decaying much more slowly. Okay, but what we're going to see, if you will, is that the frustrating thing about, it's like discretizing this stiff problem is that even though, again, after even moderate amounts of time, the solution is dominated by this term, the stability properties of the numerical method, say the Euler method in discretizing this, is going to be dominated by this much faster decaying term. Okay, and the presence of this much faster decaying term is going to end up imposing a very, very strong constraint, if you will, on how large a time step you can take using the Euler method while still getting a reasonable numerical solution. So let's see what happens. It's like to the discretization. All right. So I had said before that yn was the identity plus h times lambda to the nth power applied to y0. And then you can use this factorization to conclude the following, that this is equal to v, the identity, plus h times d to the nth power times v inverse applied to y0. Okay, and more or less it's like the reason why you can do this is because both the identity and lambda are simultaneously diagonalizable. It's like by this v transformation. Okay, all right. So let's look at this 1 plus hd to the nth power term. So of course 1 plus hd to the nth power isn't so difficult to compute, right? It looks like 1 minus 100h to the nth power, okay, 0, 0, and 1 minus 1/10 h to the nth power. Okay, so now you're starting already to see what potentially the problem is, right? So if you look again at the exact solution, the term corresponding to this first term here has this very, very fast rate of decay, right? And whereas the term it's like corresponding to the thing with eigenvalue minus 100 in the numerical method is this term here, 1 minus 1 over 100 times h to the whole thing to the nth power. So of course what could happen is that if the thing inside that parentheses has magnitude bigger than 1, then when you raise it to the nth power, of course it's like that's going to grow fast. And so it's going to grow exponentially fast. And so one has to worry then about making sure this 1 minus 100 times h term has an have an absolute value which is strictly less than 1. It's like which would then be compatible with what you would expect. It's like with the exact solution, which is that this part of the exact solution is actually decaying very rapidly. Okay. So again, more or less, it's like, you want to look at this term, it's like, and you want to sort of think about the implications it has on how large a time step you can take. It's like, well, having a numerical solution, which, again, for all intents and purposes, is decaying in both of these modes, right? You want, presumably, then that the numerical solution respects this decay property. And again, in order for that to happen, both of these terms in the parentheses have to have absolute value, which is less than 1. Okay. Okay, so let's see what happens now with the Euler discretization applied to this stiff problem. Okay, so the same way it's like that we could use the spectral factorization of the coefficient matrix lambda to write down the general solution in terms of e to the minus 100t times x1 plus e to the minus 1/10 t times x2. We can do the same thing here, and that gives you that yn is equal to 1 minus 100h to the nth power times x1 plus 1 minus 1/10 h to the nth power times x2, where the x1 and x2s are the same as the ones that were sort of there with the continuous form of the solutions. Okay, so so in the exact solution, again, it's like you have the situation where as time increases, the solutions are decaying, right? And you can ask, it's like under what conditions on the time step is that true of the continuous solution as well? So it's easy to convince yourself that in order to have the numerical solution decay as well, it has to be that the terms inside the parentheses have to be less than 1 in absolute value. So let's just see what happens when we're looking at this term. So this term is going to turn out to give you a sort of a stronger constraint, if you will. It's like on how large you're allowed to have the time step be, and still have this property that the numerical solution is decaying. This is sort of in much the same way that the continuous solution is decaying. Okay, so let's look at the condition that the absolute value of 1 minus 100h is greater than 1. All right, so this is the situation where you have blow up. Okay, and this can arise. It's like where two possibilities. One where 1 minus 100h is actually greater than 1, or the negative of that, which is minus 1 plus 100h is greater than 1. So this condition, it's like corresponds to more or less the situation where h is less than 0, and then you can check that this condition corresponds to the situation where h is greater than 1 over 50. Okay, so basically if you take a negative time step, or you take a time step which exceeds 1 over 50, then you have a situation where the numerical solution sort of grows geometrically fast, even though the continuous solution is decaying. Okay, so that's something you might want to avoid. So you might ask, it's a reasonable question, which is to say that, well, the solution looks like this combination. If you were to, you know, sort of conspire to choose the initial condition such that this x1 term is 0, then maybe things would be okay, and you can take time steps which are larger than 1 over 50, and things are still all right. Okay, so this this sort of x2 term more or less corresponds to some multiple of the eigendirection. It's like corresponding to the minus 1 over 10 eigenvalue, and then this of course corresponds to the eigendirections corresponding to the minus 100 eigenvalues. Okay, so let's consider what happens. Okay, sort of an initial condition. Y0, right, which is in the eigenspace corresponding to the minus 1/10 eigenvalue. And you can check that this happens. It's like where if, for example, y0 had the following form, 1 and 999 over 10. Okay, so you can check that this is an eigenvector of lambda. It's like with eigenvalue minus 1 over 10. Okay, so if you were to again implement the Euler method then in exact arithmetic, so if you had this, then basically what happens is that x1 becomes 0 and then x2 becomes y0. Okay, so the entire solution would be dominated by this 1 minus 1/10 h to the nth power times x2 term, at least if you were to do this in exact arithmetic. Okay, so the problem, of course, is that you don't typically do this in exact arithmetic, right? You use floating point or fixed point precision, and as a consequence of that, you have what is known as round-off error. Okay, so the devil again is in the details, right? So the basic idea is that because of round-off, right, sort of the parasitic mode right, corresponding to the sort of negative 100 eigenvalue gets excited, right, and the sort of numerical solution will still grow sort of geometrically fast. If h is allowed to be greater than 1/50, right, even though the sort of Euler method in exact arithmetic, right, would not have this geometric growth. Okay, so I should say that it's parasitic again, only in the sense that the initial conditions I've chosen, it's like mean that that particular part of the solution should not have been excited, right? So sometimes it's like one uses the term parasitic only to mean only to sort of refer to parts of the solution which really just are not emitted at all, if you will. It's like in the continuous solution. So this is nevertheless, it's like you know, one way to sort of think about these things. Okay. And in any case, it's like this example, if you will, illustrates one of the real challenges of dealing with stiff systems, because, you know, here we have a continuous differential equation where both parts of the general solution are decaying very, very rapidly. So what happens, if you will, is that the solution looks extraordinarily smooth, right? And when the solution looks smooth, it's like you don't really expect to have to take small time steps to resolve it. It's different if the solution was oscillating wildly with a very, very small, it's like a very high frequency. You know, in those situations, you might expect to have to take small time steps in order to resolve the exact solution sort of with any reasonable degree of precision. But when you have solutions which are decaying very, very rapidly, you don't expect to have to take small time steps, right? But nevertheless, this analysis shows that's precisely, it's like the part of the continuous solution which is decaying extremely rapidly, which is going to cause you, you know, to have a very, very large constraint on the time step, right? So this is an extremely restrictive constraint. It's like on the time step, you know, h cannot be greater than you know, 1/50. So so what we're going to do, it's like as the quarter progresses, then is to ask ourselves, you know, what are the properties of methods which make sense when trying to study stiff systems, and how do you go about constructing them so that you don't have to encounter these situations where, in the interest of stability, you need to take these extremely restrictive time steps. So we're going to study, in the context of this discussion of stiff systems, we're going to study numerical methods which are well adapted and don't have these extremely restrictive time step restrictions when applied to stiff differential equations. So let me stop there for now.